Hi everyone, I'm Imogen Gingell and I'm going to talk to you today about my work in shocks and transitions in space physics. And this is part of a broader topic looking at how plasma continuously ejected from the sun, the solar wind, interacts with our planets, with Earth. So let's start with a look at the magnetosphere, our local environment. So on the right here is a diagram of Earth's magnetosphere. That's the region of space dominated by Earth's magnetic field, which forms a cavity against the inflowing solar wind. So on the right here, we have Earth as a bar magnet with magnetic field lines like you may be familiar with, curving around from the north to the south pole of the magnet. And on the left, we have the inflowing solar wind with its own magnetic field, which connects back to the sun, flowing towards Earth. Now, when that solar wind impacts Earth, it's deflected, forming first a bow shock and second a magnetopause. The bow shock is the thin transition region over which the solar wind slows from supersonic to subsonic speeds, whereas the magnetopause is the boundary between magnetic field that connects to Earth and magnetic field that connects to the sun. The region I'm most interested in is this bow shock. Now, this region is directly analogous to a sonic boom formed ahead of a supersonic jet or a bullet. In our atmosphere, the gas can be slowed and heated in the shock wave by particle collisions. However, in space, the density is so low that no collisions are happening in any reasonable timescale. Instead, we need to look for electromagnetic processes which can do the slowing and the heating for us. And that's where my research comes in. So the question is, how do different electromagnetic processes contribute to heating that plasma? And to answer that question, we want to observe that thin shock layer. So there are two main methods, each of which has different advantages. The first of these is using spacecraft, which we can put in space to cross the shock wave itself and get an in situ look at how the plasma is responding. The mission I'm most interested in is NASA's Magnetospheric Multiscale, which is a cluster of 4 spacecraft about 10 kilometers apart. MMS is currently in orbit around Earth, and when the spacecraft crosses the shock wave, you get high-resolution, precise measurements of the electromagnetic fields, the electron and ion densities, velocities, temperatures, and more. When MMS crosses the Earth's bow shock, it sees something like this in the top right. You can see the very sudden rise in the magnetic field strength in the top panel and the density in the bottom panel. If we want to look at the 2-dimensional or 3-dimensional structure of our shockwave, or if we want to be able to follow the time history of structures and particles, we may need to look at a simulation, like this one in the bottom right. This simulation shows the same region of the shock as the spacecraft crossings in the upper panels. And you can see that the magnetic structure here, shown with the dark and blue lines, is very complex. Here is a video of that same simulation, and you can see that the structure is both highly dynamic and disordered. On the upstream side here, you can see waves. A little further down, there is a turbulent transition region. And finally, you see these rings of magnetic field called magnetic islands, where the magnetic field has looped back on itself and reconnected. And there's the exciting part. Magnetic reconnection is the process of changing the topology or shape of the magnetic field, which results in an explosive release of energy from the magnetic field to the particles. It can therefore contribute to heating and particle acceleration inside the shockwave. An example of one of those reconnection sites is shown in the magnetospheric multiscale data in the top right here, which corresponds to the cartoon shown to the bottom left and to the simulation frame shown in the bottom right. And that leads us to the point of the study. Ultimately, we want to know how much those reconnection sites contribute to the overall heating that is occurring inside that shockwave compared to any other mechanisms we can observe. And that brings us to the end of the presentation. So thank you very much for listening, and thanks to the STEM Village for hosting this symposium. Bye-bye.